Okay, can everyone hear me? Yes? Okay, good. Perfect. Okay, thank you for showing up. So today we will continue our discussion of binary hypothesis testing. So I just want to provide a recap before we go to the new material. So in binary hypothesis testing, we have binary hypothesis, which in this book is called X. Right, so X can take on only two values, and we would like to know what is X, okay? But we basically observe X through a conditional distribution, which is Py given X, or f of y given X in the continuous case, okay? And we observe Y. I would like to make some inferences about X. So last time we considered the Bayesian setting. This is the so-called Bayesian setting where the underlying hypothesis is such that there are prior distributions induced on it. So we know this P0, P1, and we would like to make a good decision as to whether X is equal to 0 or X is equal to 1. All right. So we came up with the so-called map rule, okay, which is simply the following. All right. You observe Y. Okay, and you would like to make the best decision. You try to find X belonging to 0, 1, all the way until m-1. Oh, in the binary case, this is simple, all right? We don't need to care about this. So in the binary case, X can only take on values 0 and 1. And in the map case, we are looking for P of X given Y, X given Y. So this is called the posterior probability, if you remember. Posterior probability. And we saw a very important result that says that the map rule actually minimizes the probability of error. This one, oh, sorry, wrong color. The map rule is very good because it minimizes the probability of error. Okay, so in the binary case, which we saw last time and we focused on last time, all that entails is to basically form the likelihood ratio, which is denoted in the book by lambda y. So that is basically P of y given X, y given 1. This is the convention. P of y given X, y given 0. That's the likelihood ratio. And we make a comparison to P0 over P1. Now, if the upper inequality is true, then we will decide that X hat y is equal to 1. Otherwise, we will decide that X hat y is equal to 0. I like to put this apostrophe here to make sure that we are deciding. Okay, so this is what we talked about last time. Another very important concept that we talked about last time, just to recap, is the notion of sufficient statistic. Okay, sufficient statistic. Now, the motivation for this is the following. Y may be very high dimensional. Okay, it could be a very long vector. Okay. It could be like y equals to y1 all the way up to yn, for example, and n could be very large. But ultimately, as you have seen from this equation here, the only thing we need to do to make the best decision is this scalar function. So we just need to use y to compute this. All right, a sufficient statistic is defined thus as any function, d of y for which lambda of y can be computed. Okay, so it is again a reduction of the dimension of y. So y could be extremely large. This is a reduction, but based on this reduction, we don't lose any information because we can still conduct our likelihood ratio test. This has a name. This is called the LRT, or the likelihood ratio test. Okay, so that's what we talked about last time, and we saw several different definitions of sufficient statistic that I will not repeat here. Okay, so that's what we talked about last time, and this time we want to switch gears and talk about the Neyman-Pearson setting. Okay, so this is the Bayesian setting, all right? Any burning questions you can ask through the chat, okay? If not, I will talk about something new. This is last week's stuff. Any questions? Also, you should have looked at some of the homework problems. So hopefully you have some practice in forming the likelihood ratio test and computing error probabilities. Okay, So if there are no questions, I want to go ahead to talk about something new, and that's the Neyman-Pearson setting. All right. So in this setting here, this is the Bayesian setting. You put priors on the underlying hypothesis, but who tells you that these numbers are actually the right numbers? All right. They could be very far off. So in order for us not to make any assumptions on the underlying hypothesis X, we avoid this situation altogether in the non-Bayesian setting or the Neyman-Pearson setting. So that is what we will focus on this time. Neyman-Pearson, also called non-Bayesian in some books. Non-Bayesian hypothesis testing. Okay. So the idea is as follows: the same setup, X is equal to, we are only considering binary, X is equal to 0 or 1. And a test, all right, a test is basically a subset of Y. Okay. So Y is the alphabet. This script Y is the alphabet of the random variable Y. Given a test and X is equal to 0, an error is made whenever Y belongs to A. All right. So what is this A intuitively meaning? What does it mean intuitively? A is the subset of Y for which we make a decision in favor of hypothesis X equals to 1. So the picture is as follows. You have this entire Y region. Okay, so your observations can only lie in this set. Nothing else. Your observations can only lie in this set. And so you're going to partition this set into A and A complement. Now, if your underlying observation lands in here, then you decide that X is equal to 1. And if your underlying observation lands in here, you decide that X is equal to 0. And that's as simple as that. Okay. So A and A complement form a partition of Y. You can write it A like this. Okay, it forms a partition. Okay, and A is the decision region in favor of X is equal to 1. Okay, so there's just some convention. So obviously an error is made. Okay, sorry. So this one move over to here. So if instead X is equal to 1, an error is made if your observation Y belongs to A. A complement, all right? Because now you are deciding that X is equal to 0 when in fact X is equal to 1. This means that you decide that X is equal to 0. Okay, so these probabilities have names. Okay, so let's denote them as Q0A. Okay, this subscript 0 actually means condition on X is equal to 0. Okay, here Y belongs to A. So this represents this situation here, X is equal to 0 and error is made whenever Y is equal to A. So this represents this probability. This has a name actually in the detection theory literature. This is the probability of false alarm. Okay, because nothing, the null hypothesis is true, but you are declaring that the alternative is true. So in the other case, however, we have this situation, all right? And this color is not very nice, all right? Let's use this color. So an error is made if X is equal to 1, but you say that X is equal to 0. So in the book, this is denoted as Q1 of A. This is probability of Y belonging to A complement conditional on the fact that X is equal to 1. And again, this has a name. This is the probability of misdetection. Okay, and this corresponds to the orange stuff on top. Okay, so these are the two probabilities. And now we notice that we are not making any assumption on the underlying distribution of X. There is no distribution of X. Is a random variable, but we do not know its prior. And how do we set this thing up? Okay, again, a very special class of tests, as you saw last time, are threshold tests. Special class of tests include threshold tests. Now, what are threshold tests? Well, threshold tests look like the following. A takes on the form all the Y's such that, okay, now I assume continuous, but it doesn't really matter if you assume continuous or discrete. There is a slight subtlety later and a very important subtlety, but we don't worry about it for now. So you are thresholding. So this is the threshold. you are thresholding the likelihood ratio. So this is nothing but the likelihood ratio that we saw just now, but we wrote that in terms of P. Hopefully you're not confused. Oh, I'm sorry, this is moving. So basically, it's just how you saw it in terms of P, but now you're looking at it in terms of F, but they are roughly the same thing. So this is called the likelihood ratio, and it's given the name lambda y. Okay, but this is a class of tests. This is a partition of the sample space. All right, this is a special class of tests. Again, this is my sample space, and this is my A, and this is my A complement. So we are saying that, okay, A is such that lambda y is bigger than eta, and here lambda y is smaller than eta. So this is a special class of tests. Now, if we use this family of tests, we will abbreviate our Qs, our misdetection and false alarm probabilities that you can see on top of this slide here. Q of eta is equal to the probability of E of eta conditioned on X is equal to 0. To be more long-winded, this is nothing but log of, oh sorry, there's no log because I like to take logs, but here we are not taking logs. Y given 1 divided by f of x given y. This is capital Y. Given 0, now we want this direction because we are making a declaration that x is equal to 1 when in fact x is equal to 0. Okay, we've got a friend joining us here. Okay, and so this is the probability of error of basically the false alarm error if we make use of a particular threshold test with threshold given at eta. So in a similar way, we can define basically the misdetection if I just replace this guy here and this inequality here in this particular way, less than 1, and this is 1. Okay, so for threshold tests, we make use of this notation. We just replace the set A with the eta. Okay, this is then understood that we are using threshold tests. Okay, so threshold tests are important for a good reason. And the next theorem is called the Neyman-Pearson theorem. And this is a major theorem in hypothesis testing. And it's also important in the context of what we are doing. Okay, so let's consider a two-dimensional plot. Feel free to ask questions through the chat, okay? In which Q0A and Q1A, all right, is plotted for each test A. For each test A. So remember that A subset Y yields a particular test. Now, among those tests, they are likely we have threshold tests, but we're going to talk about those later. So we are going to consider a two-dimensional plot where I plot these guys for every test A. Okay. Now, then the statement is as follows: for every threshold test parameterized by eta, given by threshold eta. Okay, eta belongs to 0 infinity. Eta is a positive number, and any arbitrary test A, all right, the point Q0A and Q1A, basically this is the performance. You can think of this as the performance of the particular test A, all right. Basically this point lies in the closed half space, lies in a closed half space to the top right of a straight line of slope minus eta, passing through the performance point of the threshold test Q0 eta, Q1 eta. Now, this is probably the longest theorem that we have come across this time. Okay, but so it's imperative for us to try to understand what it is saying. Okay, but in order for us to understand what it's saying, we really need a picture. Okay, so now what I'm going to do is I'm going to plot, okay, this situation here. Okay, so this is the plot here, and I'm going to tell you what I'm plotting. All right, so this is theta. I'm going to talk about what is theta in a moment. And on the x-axis, I'm going to plot theta Q1 here and sorry, Q0 here and Q1 here. All right. So Now, for a particular threshold test, we have a certain performance, which is given by Q0 eta and Q1 eta. Okay, we can achieve this particular point if I use, if I fix a pair of distributions. So if I fix a pair of distributions, okay, then what I have is the following. I can achieve this. This is for threshold test at with threshold given by eta. All right, I can achieve these two false alarm and misdetection error probabilities. Okay, so this is what I can achieve. And what this theorem is saying is that now I am going to look at a line of slope minus eta passing through this performance line. Okay, so that is my line. And yes, slope minus eta. Okay, minus eta, that is the slope. Okay, so this is the, so this eta here is the same as this eta here, which is the threshold of my threshold test. Now, here I'm only concerned with threshold tests. Okay, and I have plotted this. Basically, I fixed my eta. So this is my probability of false alarm. This is my probability of misdetection. Then I can achieve this particular point. And now I'm creating this line with slope exactly minus eta. Note that eta is a positive number, so the slope is negative. It must look like this. Okay, so this line here, the equation of this line here is parameterized by eta, and it's a function of theta. All right, so for every eta, I have a given line. Okay, so this is Q1. This is given by Q1 of eta plus eta, Q0 of eta minus theta. So let us check that this equation is correct. All right, so if I plug in theta equals to Q0 eta, then this part vanishes, it gets killed. And I'm left with this part here, which is basically this value here. All right, you agree? Okay, so if I take theta to be exactly this, okay, I take theta to be exactly equal to this, then I get basically kill this thing here, and I basically get the y value. All right, another interesting fact here is that this line here has slope minus eta. So this is the variable theta here, and the slope is minus eta. So we see that one point is correct, and the slope is correct, so the line must be correct, because a line is only characterized by the slope and one point. So we are writing down the equation of this line properly. Okay, what does the theorem say? Now that I've set everything up. So this is a particular threshold test. Okay, this is a particular performance of a threshold test. For every threshold test given by eta and any arbitrary test, the point must lie in the closed half space to the right of a straight line of slope minus eta passing through this. So now what I have is I have another test. Let's say this test is this. Okay, then basically what I have is Q0A, Q1A must lie in this region here, in this region, closed half space to the top right. Okay, this is any other test. Okay, performance of any other test must lie here. Okay, now before I go any further, actually I want to write down this particular point here. Okay, sorry, this is not the right color. This point here, all right, is what? Okay, this point here is Q1 eta, is when theta is equal to 0 plus eta Q0 eta, right? This point here, basically I substitute theta equals to 0, and then I get this exactly. All right, so now if I do the same for this particular line here, then this particular point here, I look at this with exactly the same slope, I can get this particular line. All right, and this particular point here, sorry, this is not very well drawn, is Q1A plus eta Q0A, right? So the punchline of this result is that, okay, we want both of these probabilities to be small. Okay, so we want both Q0 eta, Q0A and Q1A to be simultaneously small. So small at the same time. So this is the holy grail. The holy grail means the best possible scenario. All right. Best point. When both are equal to 0. But we cannot achieve this if our distributions are not separated. For example, if you have two Gaussians that overlap, then this is impossible to happen because the Gaussian has infinite support. However, we can use threshold tests to achieve this. The point is that, all right, threshold test, this theorem says, remark, this theorem, which is known as the Neyman-Pearson theorem, says that threshold tests achieve the best trade-off in terms of the two error probabilities, in terms of Q0 and Q1. Why? All right. You see, no matter what I choose here, no matter what eta I choose here, I can draw a certain line here. The line, the lower the better. All right. And every other test in the world has to land in this top right region. So it must be worse. Okay. So it must be worse in this sense because you are at the top right here. Any other test. So for example, if Ingrong proposes a test, okay, then the test will have performance here. If Ingrong proposes a likelihood ratio test with the same eta as me, all right, then you may achieve this. Okay, but there is nobody here who can design a test that can live here, whose performance is here. The likelihood ratio is the best. The likelihood ratio test, or threshold test as the book calls it. Okay, so the point is that the Neyman-Pearson theorem says that threshold tests achieve the best trade-off in terms of the two error probabilities. Every other test must lie here. Okay, so the proof is very simple. It follows from the proof of the optimality of the map test last time. Okay, so now we are in this non-Bayesian scenario, but we are using, actually, we are going to use a Bayesian version, a Bayesian theorem to solve it, to prove this. Okay, so now for any eta belonging to 0 infinity, okay, consider prior probabilities, note that we have no priors, but now in this proof, we are going to consider fictitious priors, P0 and P1, such that eta is equal to P0 over P1. Note that this is always possible to choose P0, P1, because eta is this positive number. So we can pick P0, P1, such that P0, P1 add up to 1, such that this is true, always possible. Okay, it's a matter of solving some equation. So now for any test given by A, a subset of Y, then the Bayesian probability of error, Bayesian error probability, is going to be given by probability of E given by the test is equal to P0 Q0A plus P1 Q1A, right? So this is nothing but law of total probability, because this guy here is the probability that you make an error based on test A, conditioned on the fact that x is equal to 0, and this probability of the fact that the test A makes an error, conditioned on x is equal to 1, right? So this is hopefully simple enough. So we can bring out P1, and what we get is Q1 with a bit of rearrangement, if you allow me to, eta Q0 of A. Okay, so this is nothing but rearrangement. We are actually moving these two around first, okay? But hopefully you allow me to skip one step here. So this is nothing but the law of total probability. Hopefully it's not too difficult. Now this for a particular test A. Now if we consider threshold test E eta, I think the E eta we write it as subscript. Okay, so let me write this carefully first. So this for any test A, the Bayesian probability is given by the above. But for any, for the corresponding, for a threshold test, it's really the threshold test. For the threshold test with threshold eta, okay, then the Bayesian, the corresponding Bayesian error probability is given by exactly the same thing, except that we have to change our notations a little bit. E eta equals to P0 Q0 eta plus P1 Q1 eta. All right, just by the same logic. So this is equal to P1 into Q1 eta plus eta Q0 eta. All right. All right, you see that? Okay. So this is again the law of total probability, because this probability of error given by the threshold test condition on x is equal to 0. And this is a probability of the error condition on x is equal to 1. Okay. And as usual, this is a probability, the fictitious probability that x is equal to 0, probability x is equal to 1. Okay, so hopefully this is clear. So I've just written down this and this, but what do we know? What do we know? All right. By the optimality, by what we learned last time, optimality of threshold tests for binary hypothesis, for Bayesian binary hypothesis testing, we know that probability of E of eta must be less than equal to probability of E of A. Right? Because threshold tests were optimal last time. Okay, threshold tests were optimal. This is due to the map rule, the map theorem that we discussed last time. Okay, but you see that, okay, you see from the above derivations here that what I have is that P of E eta and P of probability of EA, they are roughly the same. Okay, and this term here is common, so they can be cancelled on both sides of the equation. And so what I get is, so this implies that Q1 of eta plus eta Q0 of eta is less than Q1 of A plus eta Q0 of A. Okay. So what are these 2 points here? Now this point here is something that we indicated in our plot. All right. So this is the threshold guy. This is the threshold. Okay. So maybe I will have to copy this to make this absolutely clear. Okay. So let me copy this plot below, so I don't have to move up and down. Okay. So look at this point, this one here. All right. Let me get rid of all these things here. So this point here that I have that indicated in orange is this. Okay. Now what it's saying is that let us consider any other test, and it has this performance here, and this is up here. All right. So what this is saying is that these two lines, all right, so this line again has some other equation. This line has some other equation. This is H of A of theta is equal to Q1 of A plus eta Q0 of A minus theta. Okay. So what we have just shown is that the y-intercept of the arbitrary test is higher than the y-intercept of the threshold test. Okay, just by the map rule we have this, and so the y-intercept here must be bigger than must be at least as big as that for the threshold test. So basically now we conclude that the lines H of eta theta and H of A of theta. So the first one is the threshold test line. The second one is the arbitrary test. That's why it's called A. Have the same slope, have slope minus eta, and they pass through the operating points Q0 eta and Q1 eta. And Q0A, Q1A respectively. Okay. But the y-intercept for the arbitrary test is at least as high as the threshold test. Okay. But y-intercept of A is bigger than or equal to y-intercept of the threshold test with threshold eta. Okay. So we conclude that all points on the operating line of the arbitrary test lie in the closed half space, in the closed half space to the top right of all points on the threshold line, which is given by h of eta theta. Okay. So in particular, Q0A, Q1A, any Q0A, Q1A for an arbitrary test A must lie to the top right corner. Okay. Lies to the top right corner, lies to the top right of the straight line, lies to the top right of the straight line, h eta theta, for all 0 less than eta less than infinity. Okay, so this proof is a little bit confusing and a little bit technical, but hopefully the ideas are simple enough, and I'll repeat the ideas. Okay, the main idea is what I just underlined here. Okay, right. So this completes the proof, and we will discuss the implications in a little bit. But now let us look at the proof one more time. Okay, let's look at the statement and the proof. Okay, first and foremost, what is the statement? Okay, so we have the situation that we have two hypotheses and we have an arbitrary test like this. Okay, now we can also form a likelihood ratio test with threshold given by eta. It has the performance point Q0 eta, Q1 eta. All right, the arbitrary test has performance point Q0A and Q1A. All right, the problem here, right, in this binary hypothesis testing Neyman-Pearson's style, what is the problem here? Usually in optimization, we want to, for example, maximize f of x over x. Usually we want to do these sort of things, or we want to minimize f of y over y. There's only one objective function. But the problem here is that we have two things we want to minimize: the probability of false alarm and the probability of misdetection. We have two things. So when you have two things, it's impossible to minimize both at the same time. There must be a trade-off. All right. And the Neyman-Pearson theorem actually tells us what is the best trade-off in this scenario. Okay. Well, what is its exact statement? All right. So the exact statement is the following: for every threshold test given by eta and any arbitrary test, the operating point of the arbitrary test lies in the closed half space to the top right of a straight line of slope a minus eta passing through the operating point of the threshold test. Okay, so this is the operating point of the threshold test. That is my Q0 eta and Q1 eta. Okay, notice that this is the holy grail, the best possible scenario. All right, so that is the particular line that we can draw that passes through the operating point of the threshold test and has slope minus eta. All right. The claim is that every other test must lie in this space here. So it must be worse. Okay. It cannot be better. All right. So as I already mentioned, we want both the probability of false alarm and the probability of misdetection to be simultaneously small. But usually in life, we cannot have the best of both worlds. This theorem tells us that threshold tests achieve the best trade-off in terms of the two errors. Okay, so the proof is not very difficult, but it requires some thinking. So for any threshold, let us come up with fictitious priors P0 and P1, such that eta is equal to P0 and P1. Now, how do you get this P0, P1? We know that eta is equal to P0 over P1, so we can write this. And we can solve for the P0. Because eta is a positive number, no problem. All right. So for any test A, the Bayesian error probability is given by the following. This is just law of total probability. And it can be written as follows here. So I'm just taking out this P1 from here. Okay, just factoring it out. We do exactly the same for the threshold test. Then, by the optimality of threshold tests for Bayesian hypothesis testing, we have this inequality here. But by looking at the above, we see that now this one will be smaller than this one here, right? So we have this situation, this inequality. So this point here is higher than this point here. It must be at least as high. But this line here passes through the operating point of my threshold test, which is Q0 eta, Q1 eta. Okay? That means that all other tests must lie in this worst region. Remember, this is the best point. Okay? That's exactly what I'm talking about here in all the text. All right? So the point here is that all points on this line that tells us the performance of an arbitrary test lie in the closed half space on the top right of points that on the threshold line, which is h of eta. This is exactly shown here. Okay, right. So this ends the proof, and I will pause for a moment to let you deliberate on this. Okay, maybe I will go to the statement before we talk about the next idea. Okay. So in Rome, so theta represents the probability of false alarm. This represents the, This represents some probability of false alarm. Probability of false alarm. And this one actually represents probability of misdetection over on the y-axis here. Okay. So what is important is that here, this represents the probability of false alarm. And we are just considering this particular line here, right? That is parameterized, but that is fixed at a particular probability of false alarm for this particular threshold test. Okay, now I'm moving my probability of false alarm to maybe some other point here. Then we have some other operating point here for some other threshold test like this. Okay, so it is basically theta characterizes the probability of false alarm. Okay, here, theta characterizes the probability of false alarm, which will then correspond to another threshold test like this. Okay, with a possibly different slope. Okay, thank you. Okay, so actually the proof ends here. Okay, this ends the proof. So actually this comes a little bit different. So now the point is that this performance metric for any arbitrary test must lie to the top right of a straight line for all eta. All right, because just now I fixed a particular eta, but there's nothing special about eta. So already Ingrong asked, what is theta here? So the same theorem holds for yet another eta. So let's call this Q0 eta prime. And okay, so let's remove this. Okay, now I'm going to draw something else, but this must be drawn properly in order to illustrate the fact. So now I'm changing my Q0, my eta, as you can see here. All right, and I'm not going to clutter this plot here. So this is going to be my Q1 eta prime, as you can see. Okay, so now what I will have is I will have another eta. All right, so this one will extend and extend, and I don't really care where it goes. Okay, so here I will have minus eta prime here. Okay, and this is going to be true, and this theorem is going to be true for any eta. So basically all my arbitrary other tests so doesn't the slope have to be less? Yeah, sorry. So the slope has to be less. Right, I'm sorry. So the slope has to be like this. It's very difficult for me to draw. All right, pardon the drawing. The book also didn't draw this. Okay, so we have to draw this a bit like that, and so on and so forth. Okay, sorry, I drew the wrong slope, but this slope is minus eta prime. Okay, so basically all tests will lie to here. All right, so now I'm basically varying. Okay, yeah, the curve is convex and it's extremely difficult to draw on this silly iPad. So I was confusing myself. All right, so what we can say is that a point for any arbitrary test lies to the top right of a straight line for all eta. All right, and so we can define the upper envelope of this family of straight lines as a u of theta, which is equal to sup over 0 less than equal to eta less than infinity of h of eta theta. Okay, so this is given by supremum of 0 less than or equal to eta less than infinity of q1 eta plus eta q0 of eta minus theta. So that's just nothing but the definition of h eta theta. Okay, this one is nothing but this. All right, so now if you have a supremum, you have a supremum of a bunch of these are all convex things. All right, so I like to remember this situation. These are all convex functions here, at least the way I've drawn it. And if I take the supremum at every point, I get this, which is still convex. So that's the way I remember. And indeed, u of theta is convex. Okay, so the idea is as follows. All right, so we have another, let me draw another thing here just to illustrate. So that's my theta, and that's a particular operating point. Yeah, it's going to be very difficult for me to draw this beautifully, but you have one version of it in my plot, in my handwritten notes that I did a good job on paper. All right, so this is not even a straight line. So basically now we have this, maybe not so high. Okay, and this is another operating point. That is this q0 of eta 1, q1 of eta 1. This is q0 of eta 2, q1 of eta 2. q1 of eta 2. Okay, so now we have another line like this, and this is a steeper slope. So you can collect a bunch of lines. Okay, you can collect all these bunch of lines, and what will you get? You take the supremum of all these guys here, and what happens here is you will get this. This is one. There's one here. You will get something like this. All right, so that is your u of theta. Is a supremum over all these different lines. Okay, and here you should try to pass through. Right. Okay, so this drawing is not very nice. Okay, and this is actually 1 and this is 1. Okay, so what happens here is that all other tests, so you can extrapolate the theorem just now, and you see that all other tests must have operating points that lie here. Okay, the punchline is that u of theta is convex as you have all these h of eta theta is a tangent to it, and lies is a tangent to it and lies below the u curve. Okay, so the way I've drawn it, this is not very nice, but for example here, I have the u curve, and now this guy here, this line here, is a tangent to it at this particular point. Okay, so all other tests must lie here. So this actually has a name. All right, this This represents the probability of false alarm. This represents the probability of misdetection. Okay. But usually people don't draw it like this. This is Gallager's book. He draws it like this. But usually people draw the receiver operating characteristic. You may have heard of this. Operating characteristic, which is the following. Okay. The receiver operating characteristic is the following. This is the probability of detection, which is equal to 1 minus the probability of misdetection. And this is the probability of false alarm. Probabilities can only go from 0 to 1 like this. And this is the best point, and this is the best point here. It will look like this. And this is called the ROC. Okay, so this is the usual way that people draw it, but Gallager's book describes it as follows. So we will just follow this. Okay. So this is nothing but this graph here is nothing but the 1 minus version of this graph here, because here you have 1, this gets down to 0, and you have this line here. So the ROC is basically, the ROC is always concave, right? The U curve is always convex, all right? And this curve here in Gallager's book, he gives it a name. He calls it the error curve, all right? But the error curve is usually not so nice. We usually talk about ROC. Everywhere it is ROC, all right? And people also care in, for example, machine learning, they care about the AUC, which is the area under the curve, all right? So the area of the curve is a performance metric that is of great interest, and the holy grail is that the AUC is equal to 1, all right? But usually we cannot achieve AUC equals to 1. Okay, so the conclusion that I want to make here is that threshold tests are optimal points for the trade-off. Points for the trade-off. They lie on the error curve. Okay. So here, there is a very important thing I want to say, all right? So here, threshold tests are optimal points for achieving the trade-off. They lie on the error curve. For example, here, this is a certain threshold test. It lies on the error curve here, as you can see. Here, this is another threshold test. It lies on the red curve, the error curve. So I want to ask you a question here. Are all optimal tests, say deterministic tests, that means I'm not allowing any randomness in my test. Deterministic tests, threshold tests. Are all deterministic tests threshold tests? Okay. Are all optimistic tests threshold tests? So for example, if I want to achieve every point on the error curve, does it suffice for me to use a threshold test? There's a difference in the statements that I made, okay? So one of the statements that I made is that all threshold tests lie on this red line, the error curve. All threshold tests lie on the red line, the error curve. But are all points on the red line corresponding to threshold tests? Are there any holes in the red line for which you cannot use a threshold test to achieve it, and you need to use something special? Okay, so the answer here is surprisingly no. All right, there are some other tests, all right, that we have to use in order for us to achieve all points on the error curve. Okay, we need mixtures, okay, of threshold tests. As the next example shows, we need mixtures of threshold tests. So I will try to describe what are mixtures of threshold tests, okay, through an example. All right, so hopefully the statement is clear. this statement is clear. This is super important. Threshold tests are optimal points for the trade-off. They lie on the error curve. Okay. So if I have a threshold test, it must lie on the error curve. But then the curve could contain many other points that may not be attainable by a single threshold test. You may need to use mixtures of threshold tests. All right. So let us look at an example to really see that there needs to be more needs to be done. Okay. So now we have the following very simple situation: binary symmetric channel. All right. It's an information theory thing. Y, X can take on two values, 0 and 1. Y can take on two values, 0 and 1. Now, Y is equal to X with probability 2/3. And Y is not equal to X, of course, with probability 1/3. Okay, so the transition is as follows. So here, Y equals to X is 2/3 if X is equal to Y, and if X is not equal to Y, this is 1/3. All right, this is a summary of the binary symmetric channel. Okay, so let's look at a particular threshold test, and let's actually draw the whole error curve to make it clear. So the threshold test has the form lambda of Y is equal to P of Y given X, Y given X, Y given 1, P of Y given X, Y given 0 compared to eta 1, and this declares 0. Okay, now in this very deterministic scenario, right? In this very deterministic scenario, okay, first we know that Y can only take on two values, 0 and 1. Then how many values can this take on? All right, so it can only take on, so this guy here can only be take on 1/2 or 2. Right, this ratio can only take on 1/2 of 2. All right, because, well, it can also take on 1. What am I saying? So this ratio here can take on three values, 1/2, 1, and 2. Why is that so? If the top here is equal to the bottom, then this is 1. Now the top here could be 2/3, the bottom could be 1/3, in which case this is 2. The top here could be 1/3, the bottom here could be 2/3, in which case we have 1/2. All right, so the likelihood ratio can only take on three values. Y can only take on two values. Okay. All right, so let's just keep all this in mind that this problem is a little bit discrete. Okay. So, right. So, but in fact, more can be said. In fact, when Y is equal to 1, then let's calculate this exactly. Lambda of 1 is equal to 2/3 over 1/3, which is equal to 2. Instead, when Y is equal to 0, lambda of 0 is equal to 1/3 over 2/3, which is equal to 1/2. All right, hopefully you can follow this calculation. For example, when lambda I evaluate at 0, so this is 1/3 because the symbols are different. And here, the symbols are the same. So 1/3 over 2/3, which is equal to 1/2. So now, suppose now my threshold is either equals to 1. This corresponds to maximum likelihood decoding. All right. So what will we choose? What will we choose? So the test will become the following compared to 1. All right. So what will we choose? So if Y is equal to 0, what will we, if Y is exactly equal to 0, what will we decide? Okay. Now, here I want to make clear that here we decide in favor of X is equal to 1. Here we decide X equals to 0, just to be clear. Now, if Y is equal to 0, if Y, say, let me do this one slowly. If Y is equal to 0, this guy here is equal to 1/2. So what would I choose? I would choose X is equal to 0, right? All right, so this guy in this situation here, if Y is equal to 0, X hat will be chosen to be 0. Conversely, if Y is equal to 1, so now in this case here, Y is equal to 1 and this will be equal to 2. So I will take the top clause here, right? I will choose X hat is equal to 1. So just to summarize this, I will choose X hat Y is equal to Y. X must be equal to Y. X hat must be equal to Y in this case here. So that's maximum likelihood decoding. All right, this is maximum likelihood decoding. Right. So no one says that our eta must be equal to 1. No one says that. All right. So if, however, eta is less than or equal to half, okay? If this is less than or equal to half, then what will happen? Okay, then what I will have is that my test looks like this. Eta, all right? And this eta, we know that it's a number that is less than or equal to half. Okay, here I'll decide x equals to 1, and here I decide x is equal to 0. Okay, so what will I choose? All right, what will I choose? Well, it will be easy to see that under this scenario, I would always choose x hat y equals to 1. All right, because this guy here is very small. Think of it as like 1/4. And this guy here can only take on 2 values, this and this. So this inequality, this side here is always satisfied. This is very small. This one is at least half. So we always have this inequality here. So we have this. Don't worry about what happens at the boundary of this equal here. Don't worry about that. But you just need to worry about this conclusion. Okay, so this implies this. Now, in the final case here, if eta is greater than 2, now you know what happens here. So this one I have to compare to eta, which you know is bigger than 2. All right. So this here is very large number, say 3. Okay. But this guy here is at most 2. So this inequality dominates. This inequality dominates. And so you will always declare, x hat y will be equal to 0, no matter what y is, for all y here. Okay? For all y. Right? Okay. Right. So the decision is the following. All right. The decision is the following. So the final decision is the following. So x hat y is equal to 3 choices. 1, if eta is less than or equal to half. 0, if eta is bigger than 2. And in between here, it should be easy to verify. Okay. Less than or equal to half here. Y. It should be easy to verify like this. Okay, now we have to take a certain convention for what is the meaning of equal here. But once we fix the convention, we will fix the convention here. So don't worry too much about it. Okay. Hopefully this is clear. All right, this is really important for us to decide the rule. So let me go through this again. We have the binary symmetric channel with crossover probability 1/3. So this is the channel, if you wish. Now, the threshold test always take these forms. All right. When y is equal to 1, then the likelihood ratio is equal to 2. When y is equal to 0, the likelihood ratio is equal to half. All right. Now, under maximum likelihood decoding, which means eta is equal to 1, then this guy is equal to 1. All right. Now, it is not easy to see that this is true, right? Because here, this is equal to, if y is equal to 0, then I would decide that this is half. And so half is less than 1. And so I will make this decision leading to this. Now, if y is equal to 1, then this guy here is equal to 2. So this inequality holds. And so x must be equal to 1. I take the rule above. Okay. So if eta is say greater than 2, let me consider this scenario. So this guy here is like 3. Think of it as 3. Okay. But this guy can be only at most 2. Okay. So this inequality dominates, and we always decide that x is equal to 0. So I'm not going to go through this. The final rule is this. Okay. So our job now is to calculate the error probabilities. Okay. So for eta less than or equal to half, all right, as we have seen here, x hat y, so here I think you need to put this, x hat y is equal to 1. So for both y equals to 0 and y equals to 1, error is made for x is equal to 0. Okay, but not x is equal to 1. So here we make an error for x is equal to 0 because we always declare 1. Okay, we always declare 1. So Q0 of eta here in this case is 1, and Q0 of eta, right? So this is eta is less than or eta is less than half. So we have Q0 of eta is 1, and Q0 of eta, this should be Q1 of eta is equal to 0. Okay, for eta is less than equal to half. Okay. So why is that so? Because here this is the probability of false alarm. Okay, so under the underlying hypothesis is x equals to 0, we definitely make an error for both y equals to 0 and y equals to 1. So this is equal to 1. So we always declare 1. So this one is equal to 0. The misdetection is equal to 0. Is the probability of misdetection. Okay, this is the probability that the underlying hypothesis is equal to 1, but we make an error. But we never make an error when x is equal to 1 because we always declare 1. Okay, so underlying hypothesis is x equals to 1 here. We always declare 1, so we never make an error here. Okay, so now, so in the intermediate case for half less than eta less than equal to, we know that we are doing maximum likelihood decoding essentially. Okay, so Q0 of eta is equal to Q1 of eta by the symmetry of the problem, and is equal to 1/3. All right, why is that so? If you look at the channel here, all right, you will see that you will decide, in the maximum likelihood decoding case, you will decide what is x based on what is y. Right? If y is 0, you declare x is 0. If y is 1, you declare x is 1. Okay? So when do you make an error? You make an error when this flips. Okay? Which means 1/3, 1/3. Okay? Now, finally, for eta greater than 2, okay, for eta strictly greater than 2, we know that x hat of y, we always declare for this for every y is 0 or 1. So we don't even look at the observation. We say that x hat is definitely equal to 0. Okay? So now in this case here, Q1 of eta is equal to 1. We always say 0. So the probability of misdetection is equal to 1. And Q0 eta is equal to 0. Okay? So now what is our, so now hopefully you understand this. Is there any question here? Okay. So just want to repeat this. This is nothing, this is the following. Okay, why is this equal to 1? Okay, what is the meaning of this? The probability that we decide that x is equal to 0 when x is equal to 1. But this is equal to 1 because we always declare x is equal to 0 when eta is bigger than 2. Okay, so this comes about because of this rule here. Okay, and of course, conversely for this one, I will not explain. All right. So in this corners case, we have the reverse of this scenario here. We have the reverse of this. Okay. So now we are ready to actually do our error plot. Okay, our error curve. So let us summarize our findings. So Q0 of eta is equal to what? We have 3 cases. 1, 1/3, 0, when eta is less than or equal to half, when eta is between 2 or half, and when eta is bigger than 2. Here, Q1 of eta is equal to roughly the same things, so I can copy this. Okay, paste here. Okay. And it's exactly this, but these are flipped here. 0, and 1. Okay. Right. So now we are ready to make our error plot. All right. So basically this part here is this Q0, Q1, we are basically just summarizing our results in what we have done in this calculation that we have done previously. Okay. So what we have done is we have taken eta to be from 0 to infinity. Okay. And based on the particular eta, we have come up with our decision. This is our decision. And based on our decision, we have been able to compute Q0 and Q1 based on the range of eta. Okay. And it is summarized here. So we are now able to make our error plot for this particular case. Okay. We are now ready to make our error plot. So this is the Q1 and this is Q0. And what is happening here? All right. So this is 1 and this is 1 and this is 1 and this is 0. So where are our operating points? Okay. So let's see here. So we have a point 1, 0. So for this point here, 1 and 0 gives this point here, 1, 0. All right. For the last one here and here, we have this point here. Okay. And we have 1/3, 1/3, right? So this is probably 1/3 here and 1/3 here. We have another point, which is this point here. Okay. So hopefully this is nice. So this is actually what we have. Okay. Right. These are all the points that threshold tests can achieve. All the points that threshold tests can achieve. Because for every threshold, we have found the rule, the decoding rule. And after we have found the decoding rule, we have found the 2 error probabilities, okay, given by this. And we have plotted this for all thresholds, and all thresholds can only yield this. But remember that we are interested in the error curve, which is given by, all right, supremum over all eta running from 0 to infinity of h of eta theta. All right. So here, for example, where are our lines? Okay. So we will have one of these etas like this. Say this is eta equals to 1. All right. And here we probably will have one of these etas. Okay. And another eta over here, another slope over here. Okay. So what is the supremum? What is the supremum? Okay. So these are for different eta. So for example, here we have eta equals to 1/4. Here, this represents the point when eta is 0 less than eta less than half. We have this operating point here. Here we represent eta bigger than 2. And here we have the case when half is less than or eta less than or equal to 2. Okay. So we have all these different lines here. For example, this could be eta equals to 4. So we have a steep slope here. So if all goes well, we are ready to plot our error curve, which is nothing but this, as you can see. And hopefully it is nice and convex. So this is actually our u of theta. Okay, our u of theta. So the point here is that, all right, threshold tests attain the points A, B, C. Okay, so A, B, C here. Threshold tests attain this, as we have seen. But these points are a very small part of our error curve, which is the curve in blue. Very small part. Because the error curve is this entire blue thing here, right? This point here, for example, all right, is not attained by a threshold test, right? Threshold test. Okay, so basically what I want to say is that the error curve contains actually many points that are not achieved by threshold tests. By threshold tests. Okay. For example, an interior point between 1/3, 1/3, and 1/0. Okay. So for example, if I have this special point here, all right, this special point here, this is not attained by a threshold test. Okay. So the point here is that we will have some particular points that are not attained by threshold tests, unfortunately. Okay, so usually, how do we make use of this error curve? How do we make use of this error curve? Okay. Now, often your boss will tell you, I can tolerate a probability of false alarm of 1/3. Okay, maybe not so big, but for this example, say 1/3. I can tolerate. So your boss will tell you to design a system, the requirement is that the probability of false alarm, which is equal to Q0, is less than 1/3. All right. We would like to, our goal is to minimize the probability of misdetection, which is the Q1. Okay, so we go to our error curve and we look and see. Now, so our boss tells us that the probability of false alarm should be less than 1/3. This is the system requirement. So we can only operate to the left of this part here, right? Because this is my probability of false alarm, we can only operate to the left of this point. Now, to the left of this point, which is the best point that you can operate in terms of the probability of misdetection? Obviously, this point, because that's the smallest among all the points here. Okay. If the requirement is that the probability of false alarm is less than 1/3 and you want to minimize the probability of misdetection, then the answer is 1/3. Now, you will be very dumb if your boss tells you you can operate here in this region and you operate at this point, because your probability of misdetection here is 1. That's very bad, right? That's very bad, right? So usually we make use of the ROC or the error curve in this fashion here. Okay, we want a desired probability of misdetection or for probability of false alarm, and we want to minimize the probability of misdetection. So we look at the error curve and we eyeball the point that we want to operate at here at this point. But now this number is chosen very nicely, right? 1/3. So now I want to tell you the most important thing that I want to tell you today. All right. So what if this number is not 1/3? For example, your boss tells you that he wants a very stringent probability of false alarm. For example, he wants probability of false alarm at here, 1/10. All right. Then you somehow want to do something like this, right? All right. You don't want to do this still. But if you are only required, you only have at your disposal, you can only use threshold tests. Your boss tells you that the best false alarm probability is 1/10. All right. You should be operating here. But if you only use threshold tests, you can only operate at these 3 points. So you can only operate at point C. That is very bad because your probability of misdetection is 1, when instead it can be strictly smaller than 1. Okay. So the idea here is that now our requirement on probability of false alarm may not be in 0, 1/3, 1. Okay. So we want to achieve, but nevertheless, we want to achieve the best, which is the smallest probability of misdetection, which is Q1A, for a given probability of false alarm, which is this Q0, Q0A over all possible tests that are, say, less than equal to half. All right. So if less than equal to half, say here, your boss tells you probably your false alarm can be less than equal to half. Now, you can use this threshold test here, but it seems that you can do better, right? You can do better because you can achieve this particular point here, right? Which is strictly smaller than 1/3. And that is the point that you should do, you should use. So the idea here, in this case here, is to randomize. Okay, let me write this properly. The idea here is to randomize between two tests. Okay, that is x hat y equals to y. This is the ML test, and the test x hat y, which is always equal to 1 for all y. Okay, now this guy here use the operating point 1/3, 1/3. Let's say Q0, Q1 equals to 1/3, 1/3. Now this use the operating point Q0, Q1 given by 1, 0. So now what we have is we want to randomize between this point and this point because our boss tells us that the requirement is that the probability of false alarm is less than or equal to half. Okay, so now let me maybe instead of jumping up and down, okay, I will draw this picture again. Okay, right, so let me draw this picture again. It won't take too long. Maybe I'll use a different color. It won't take too long, so let's do it. So we can threshold test can achieve these particular points. It can also achieve this point 1/3, 1/3. This is Q1, this is Q0. So now what we can do is we can actually look at all these points. This is basically the error curve. Okay, and now our requirement is the following, right? Q0 is less than equal to half. So I am required to look at this side here. I am only allowed to operate over on this side. Okay, so that is the requirement. Okay, so the idea here is to randomize between this point here and this point here. But how to randomize? All right, so one of the Q0s is equal to 1. Another Q0 is 1/3. 1/2 is in between, right? 1/2 is in between. So the idea is as follows. So our requirement is that Q0A is equal to 1/2. So I'm going to consider alpha fraction of the time. I'm going to use this test here. That gives 1. Plus 1 minus alpha fraction of the time. I'm going to use the ML rule, which gives 1/3. Okay. And so we have to basically look at a convex combination of these two tests, this test and this test. And we see how often we use one of the two. All right, so now if you solve, right, for this equation, we get alpha is 1/4. I'm not going to tell you how to solve this equations. So our final decision is the following. It's a convex combination of two rules. All right, it is x hat y equals to, now let me write this down in 3 cases. 1, if y is equal to 1. Note that under both rules, if y is equal to 1, I will definitely say 1. The ML rule says so. Here, I always declare 1. So in the ML case, if y is equal to 1, we say 1. In here, we always say 1. Always. All right? So that the probability of false alarm is always equal to 1. All right? So here, y equals 1, we always say 1. Right? Now, the only issue is when y is equal to 0. Under the ML rule, we say 0. But under the other rule, we say 1. Okay? So here under the ML rule, let's say z is equal to 0. Okay, I'll explain what is z in a moment. Here we say 0 and here we say 1. All right, so z here is a certain Bernoulli random variable with probability alpha equals to 1/4. So that is the alpha, which is equal to 1/4. And here the probability z is equal to 1 is equal to 1/4, and probability z is equal to 0 is 3/4. Okay. So what happens here is that we will use the ML rule. Okay, so alpha, what does alpha represent here? Alpha represents the fraction of time we always declare 1. Okay, so in particular, 1 minus alpha, this is 1 minus alpha, 3/4, is the fraction of time we use the ML rule. Okay, so when we use the ML rule, if y equals to 0, we say 0. And we use this 3/4 of the time. All right. Now, in the remaining 1/4 of the time, we use the always declare 1 rule. So I don't even look at this. I always declare 1. Okay. So this is the ultimate rule that we will use. We need to have an additional source of randomness here in order for us to achieve all points on the error curve. So this is the error curve. If we want to achieve this point here, so we want to achieve this special point here, what do we deduce? All right, we flip a coin with probability, we flip a coin, let's say z, with probability z is equal to 1 is equal to 1/4. And if z is equal to 1, okay, sorry, if z is equal to 1, then we will use which one? We will use operating point A. If z is equal to 0, we use operating point B here. So is this clear? I think I described this very carefully. Is this clear? This is the most important thing today. All right, I will repeat this. This is a very long example, but it is very important. Okay. Now, so why did we do this example? All right. We did this example after we saw that threshold tests are very good. They are very good in a certain sense. They are optimal points for the trade-off. So if I have a certain ROC or a certain error curve, I know that if I have a threshold test, it lies on the error curve, right? But the error curve could contain many other points that may not be achieved by a single threshold test. The purpose of the example is to show that every point on the error curve is attained as a convex combination of 2 threshold tests. Okay? At most 2 threshold tests. So this particular example illustrates that I have a binary symmetric channel. By varying the eta, I obtain the rule. Okay? I obtain the rule for all possible values of eta here, all possible thresholds. Then I obtain these error probabilities. This is the false alarm and this is the misdetection. Then I was able to plot my error curve here. And I saw that in my error curve, only 3 points are attained by threshold tests. All these other points are not. And hence we are forced to do randomization. Okay? If we want, for example, our boss tells us 50% of the time we can have false alarm. So we must operate here. Then we somehow need to mix these 2 guys. We need to toss a coin. If the coin turns out heads, we use this one. If the coin turns out tails, we use this one. So basically, our performance now would be exactly at this point here. We will get 1/2 false alarm. And what is our best misdetection? The best misdetection or Q1 probability would be equal to what? Well, it will be nothing but 1/4 times 0. So because this guy here is 0, okay, the y-axis 0, 1/4 of that, and 3/4 of what? 3/4 of 1/3. which is equal to 1/4, which is less than 1/3. So you do better and your boss is happier. Is that clear? If we use this rule, we can do better than a threshold test. Because threshold tests can only attain 3 points on this curve. But if I do a mixture of threshold tests, I do this, okay? So basically I can create this point here, 1/4. Cool, right? Cool, right? Now I cannot see your face. When we require a point lies on 0, how do we understand it's still optimal? In this condition, threshold will be infinity. So the threshold, yes, I understand this. Okay, so yeah, here not quite 直线. You see this point here and this point here, the threshold may not be infinity. So this point here, maybe I go back to this picture. So here, this point here, the threshold is anything from here to here, not infinity. Here, the threshold is anything bigger than 2. 3 is okay. So it's not infinity. All right. Here, the threshold used is here. Here, the threshold used is eta bigger than 2. Understand? 直线. The slope may be infinity, but never mind. You see. Okay. So this sort of scenario where you have to use randomization, remark. Okay. Okay. First remark is we need to use randomization or flip a coin to attain all points on the error curve or ROC if the likelihood model is discrete. Model is a PMF. Okay, i.e. P of y given x dot given x is a PMF. I.e. it can only take on finitely many values or countably many values, countably, okay? So later we'll see another example. It's a PMF for each x, okay? For all x. X between 0 and x is only 0, 1, okay? Number 2, okay? The reason why we have this line here, this phrase here, is because you see, look at this example here. Okay, look at this example here. The reason why we have only these discrete points is because our likelihood is discrete here. The channel model here is discrete. All right. Now you can easily convince yourself that I will write another statement here. If f of y given x dot given x is a probability density function. All right. No randomization is needed. No randomization is needed. And the error curve, and sorry, let me say it properly. Every point on the error curve on ROC or error curve is attained by a threshold test. So I'm not going to prove this, but it should be intuitively clear that if you have densities, all right, if you have densities, nothing bad can happen in the sense that your ROC or your error curve is such that every point can be attained by a threshold test. You have all these discrete points here because your y in this particular example is discrete, unfortunately. Okay. No. Jing Yang, randomization or test improves the false alarm error probability. Right? You see here, misdetection probability. So sorry, your boss tells you that he is satisfied with probability of false alarm less than half. Okay. Now, if you use a threshold test, okay, so you must operate here. Your boss tells you that you must operate here. All right. If you only insist on using threshold test and you have no coin in your hand, So you cannot generate extra randomness. Then the best you can do is this, and your misdetection is 1/3. Okay. Now, if you have one coin in your hand or a MATLAB randomizer, all right, then what happens here is you can flip a coin with the correct randomness here, okay, and you can actually attain a better misdetection. 1/4 is smaller than 1/3, right? So your boss will be happier, right? And in fact, we can calculate exactly the best misdetection probability. Yeah, so we can do better. Okay. And one thing you want to learn out of this class is that what are the fundamental limits? When can we do better? When can we not do better? Okay. All right. Cool. Okay. Now, this is a general, thank you for the question. This is a general principle, right? So the more resources we have, the better we can do. The less resources we have, okay, if I give you more resources, you can only do better, right? If I give you a coin versus I don't give you a coin, you can do better if you have a coin of the right bias, okay? So if I give you a coin, you will be able to randomize between these two. Oh, sorry. You will be able to randomize between these two things. If I don't give you a coin, you are forced to use this, okay? Because you have more resources, so you can do better, or you don't know worse, all right? Now, this is also true in other problems. If you have shared randomness in some secrecy problems, then you can do better, okay? If you don't have enough shared randomness, you cannot randomize your secret, all right? So this is something that I work on. All right, so I want to go through one last example. I don't want to go through the Gaussian example. I've typed that out. I want to go through another randomization example for countably infinite alphabets. Okay, so in the last half an hour, I will go through another example and we will call it a day and we will talk about estimation next time. Okay, so in the last example, we have the following situation. Okay, we have that. So example, all these examples are typed out in leg10.pdf. Today is lecture 10, yeah, so it's leg10.pdf, okay? Or leg 10 or leg 11, something like that. All right, so I typed this all out. So under x equals to 0, all right, we have a certain parameter q, which is equal to q. Notice that this q has got nothing to do with the q above, sorry, all right? But this is a legacy issue. Half, under x equals to 1, q equals to q1, this is some parameter equals to 1/4. Okay, some parameters. Sorry, this q, these qi's are not the same as above. Same as the above probabilities. A legacy issue. Sorry, but you all should be able to differentiate. The likelihoods are, okay, p of y given x. Okay, y given x is equal to y is equal to 0. Okay, is equal to q0 1 minus q0 y, where y is greater than or equal to 0. So this is a geometric that starts at 0. A geometric that starts at 0, and p of y given x, y given 1. This is q1 1 minus q1 y, y greater than or equal to 0. So what's the first thing that you should check before I start talking? We need to check whether this question I'm giving you makes sense. All right. I'm always a bit wary when I work with geometric distributions, because geometric can start from 0 or 1. Hopefully, by the end of this class, you realize that. That's why in Wikipedia, when you go to geometric distribution, you have this column here that says start from 0 or start from 1. Okay, and this is very tricky. Like, for example, it tricked Priscilla. All right, because sometimes you need to do -1 here, sometimes you don't, but the best way is you check that this adds up to 1. So we sum over all y bigger than or equal to 0 of q0 1 minus q0 power y. And we see that, okay, this is q0 over 1 minus q0, which is 1. So fortunately, these are two proper distributions. Okay. And now we see this is a difficult problem because these are discrete distributions. All right. So we may have to do randomization later on. Okay. All right. So, all right. So first problem here. So under the ML setting, so this is P0 equal to P1, this maximum likelihood eta equals to 1. The question is to find the minimum probability of error rule. Okay, so this is one of my, I think, previous exam problems or a problem that I designed for an exam, but I decided not to use it because I got a better idea. Okay, anyway, so I have these two likelihood models, and now I want to find the minimum probability of error rule. So the likelihood ratio, let's say L of y, or lambda of y, I think that's the notation that we use. Lambda of y is P of y given x, we put the 1 on top always, over P of y given x, y given 0. So we put Q1, 1 minus Q1 y over Q0, 1 minus Q0 y, and we compare it to eta, which is equal to 1 in this case. All right, here we declare that x is equal to 1, and here we declare that x is equal to 0. Okay, so now plugging the numbers in, which I will probably not do. Okay, we will have so Q0 is 1/4. So 1/4, 3/4 power y over 1/2. All right, power. So okay, Q1 is this 1/2 power y plus 1, I guess. Okay, this looks a bit strange. Am I doing things the right way? Yeah, I think it should be roughly right. Okay, so here we declare x equals to 1, and the bottom we declare x equals to 0, 1 here. So you can take logs on both sides. I'm not going to do it. Okay, so if y is bigger than or less than log of Q0 over Q1 over log of 1 minus Q1 over 1 minus Q0. Okay, here we decide x equals to 1. All right, so that's the rule. But after you plug in the numbers, which I will not plug in, you can check that if y is bigger than less than 1.71, here we decide x equals to 1. So of course, y can only be an integer. All right, y can only be an integer. So we decide in favor of x equals to 1, the alternative hypothesis if y, our observation, is bigger than or equal to 2. And of course, we decide in favor of x equals to 0 otherwise. Okay, so that is our rule. Is greater than or equal to 2, so less than 2. Okay, so these sort of things are standard. These sort of standard exam problems for hypothesis testing. And it's also very important in real life. You need to know how to conduct a likelihood ratio test in real life. Okay, 2. So the second part of this problem consists of, okay, so this is plot the probability of false alarm, probability of detection. So this is 1 minus Q1. The Q1 is the Q1 from the previous. Okay, now let me not make a big deal of this. This is 1 minus probability of misdetection. Okay, plot the PF-PD curve. This is called the ROC curve. All right, this is more important. Okay, PD is 1 minus PMD. Okay, so particular PD is equal to 1 minus Q1A, where this is the notation in the book that I think no one else uses. All right, so maybe I should write my own book. Okay, so right. Okay, so now we have to plot the PF and PD curve, right? So what is the probability of false alarm? All right, that is the probability that y here, as you can see here, all right, no matter what you do, the eventual likelihood ratio test will be a test of y against an integer. So if you change this guy to say eta, all right, change this guy to eta, this number will change. Okay, it should be easy to see after you take logs on both sides. All right, you take logs on both sides. If it's eta, you take log. So no matter what you do, you will basically threshold the y. You will basically threshold the y. So let's say our threshold of y is called gamma. All right, because usually the threshold for the lambda is called, because usually the threshold for the lambda is called eta. So now I'm going to use gamma as a threshold for y. So this is this. Okay, so there's a probability of false alarm if I make a threshold on y that is called gamma. So that is nothing but if I sum over all possible values of I, okay, bigger than or equal to gamma of Q0, 1 minus Q0 power I. Okay, why? Because under Q x equals to 0, this is the probability measure. This is the probability mass function of interest. This is the probability mass function. And the event here is I'm looking at all possible y's. Maybe I make this y not to confuse you. Y's that are bigger than or equal to gamma. Okay. And now if you plug the numbers in, you see this is y bigger than or equal to gamma of half of y. And so you can bring out half. And so this is how to do this. Over 1 minus this. So this is half to the gamma. Right? I mean, this is just an arithmetic that I'm not going to belabor the point. Okay. So for if I fix my gamma as the threshold of y, then I get a false alarm of this much. Now, what is my probability of detection? The probability of detection is 1 minus the probability of misdetection. So here is x equals to 1 and y is bigger than gamma. Notice that I always declare that x is equal to 1 if y is bigger than something. Okay, so this is my acceptance region for x equals 1. This is my acceptance region. Okay, here x equals 1. This is the probability of detection. Okay, so this is the probability of detection. So now we have to sum over all possible values of y bigger than gamma of the probability measure corresponding to x equals to 1, which is equal to q1, 1 minus q1 raised to the power of y. Okay, this is the probability distribution when x is equal to 1. And so after all is said and done, all right, I'm not going to do all this algebra, you will get 3 over 4 to the power gamma. Okay, so these are all arithmetic that I'm not going to talk about. The ROC, which is the set of all PF, PD, PPF, PP. Sometimes they call PFA, sometimes they call PF. But never mind. Point is the countable set. The let's say countably infinite, to be more precise. Set, okay, of pairs of points as I vary gamma, pairs of points as I vary gamma. So now I have PF. Sometimes I do PF, sometimes I do PFA. PFA, PD equals to, well, now I change my gamma. Okay, gamma can be running from 0 onwards. Okay, 0, 1, 2, 3, 4, and so on and so forth. All right, so as I vary gamma, these guys here are going to vary as well. So let me just calculate them. So here I have 1, 1. Okay, and here if I have 1, I will have half 3/4. And here I will have 1 over 4, 9 over 16. Okay, and if I take the power of 3, I have 1 over 8 and 27 over 64. All right, and I do not know whether I can continue. What is the 3 to the power 4, 4 to the power 4? This is 256, I think. This is 81, right? And so on. So this is the ROC. Okay, so just to draw it out, if I can draw it out properly, let's see. Okay, so this is my PD, and this is my PFA. Okay, and if I have my gamma be at 0, now the point that I am going to operate at is this point, 1, 1. Okay, the next point is 1/2, 3/4. This is 1/2, and 1/2 here, 3/4 here, maybe here. This point here. Okay, and the next point is 1/4, 9/16. This is 1/4 here. What is 9/16? This half, this is 3/4. 9/16 is slightly more than half, right? Yeah, so I see here. And 1/8 and something. And say somewhere here. Doesn't really matter where. So our arrows, these are the points that can be achieved by threshold tests. Okay, and we have a bunch of points here. These are a bunch of points that can be achieved by threshold tests, and my ROC will be the piecewise linear version of this. Okay, this is supposed to be linear. Okay, and so on and so forth. Okay, so there's my ROC. Cool, right? Okay, so these are bigger. These are the black points are the points that can be achieved by threshold tests. So notice that now my geometric random variable is a discrete random variable supported on a countably infinite alphabet. And so now I will also probably have to do randomization. Okay, so now my boss tells me, part 3. Okay, find the maximum probability of detection or the minimum probability of misdetection subject to the fact that probability of false alarm is less than or 1 to 8. So this one you'll notice that is 1/2 to the power of 7. Very nice, right? Very nice. This is a nice number. All right. So this is the question. So you want your boss asks to design a hypothesis test that achieves this false alarm rate of 1/2 to the power 7, but he or she wants the maximum PD. So now you can go to this curve and you can continue drawing this, right? But we don't really have to. By the way, this gamma equal to 0, gamma equal to 1, and so on so forth. So everything here in between is gamma. Here, gamma between 1 and 0, and so on and so forth. Okay, so you can go to this curve and you can check where is this and read this off. All right, 1, 2, 8 is somewhere here. You can go and read off the y-axis, but we don't really have to, right? That's very painful, right? So if PF, probability of false alarm, is allowed to be less than 1 to 8, then we choose our gamma to be equal to 7, right? Because all our probability of false alarms look like this. And if I want 1/1 to 8, I will choose gamma equal to 7, correct? Yes, gamma equal to 7, right? And the corresponding probability of detection will be equal to 3/4 to the power 7. All right, that is the best possible. Okay, so that is that. Okay, the best probability of detection is this much. Okay, so the rule is as follows. All right, if the y is bigger than 7, declare x equals to 1. Conversely, if y is less than 7, that means 6 and below, then we will declare x is equal to 0. Okay, so now we are, for this particular problem, we basically just read off the ROC. Just read off the ROC here. Look at the ROC, where is 1/128, and we read off here. That will be the best probability of detection. Okay, so that is a hopefully simple problem. Now in the last 10 minutes, I will not be so simple. All right, if you look at my the questions that I asked, I never asked all these benign questions here where you have this very nice 1/2 to the power 7. So you can choose a beautiful threshold like this. So we need to do a little bit more. Okay, so now for part 4, find the maximum probability of detection subject to probability of false alarm less than or equal to 1/100. Now this is not going to be a dyadic rational of 2, right? It's not 1/2 to the power k for k integer. It's not. So we have to do a little bit more work. All right. Okay, so this is again this and find the rule. Okay, so this is the first part, and find the decision rule. Okay, so this is just another example to show you that in fact this sort of phenomenon is not special to distributions that are supported on finite alphabets. It could be supported on countably infinitely many alphabet, countably infinite alphabet, like geometric distribution. Okay. Okay, so let's do this. Okay, so you notice that first you note this is the answer. 0.01 is between 1/128 and 1/64. This is 1/2 to the power 7 and 1/2 to the power 6. So we need to randomize between operating points given by 1/2 to the power 7, 3/4 to the power 7, and 1/2 to the power 6, 3/4 to the power 6. We need to operate between these 2 points. Okay, so now the way to decide, okay, so here I must tell you something. If I'm very evil, I will not tell you. So here you are allowed to use a coin of you're allowed to use a coin of any bias you like. Bias means the probability that the coin is equal to 1. Okay, any bias. If I tell you you cannot use a coin, that's another question. All right, then you can do the other question as well. All right, so the probability of false alarm is equal to 0.01, which is 1 out of 100. So you need to randomize between 1/128 and 1/64. You need to choose this alpha properly. And I am not going to do this arithmetic. I'm just going to tell you that alpha is 0.72. So the maximum or the best PD is going to be alpha times the corresponding 3/4 to the power 7 plus 1 minus alpha to the 3/4 power 6. And that is something 1459. Okay, so that is a way to do this sort of problems. We try to find the best combination, or the best convex combination of this probability of false alarms. And we saw that this is necessary because our space, our observation space, is a countable set. All right. So basically our decision is as follows. Our x hat is equal to what? Okay, so it's equal to 1 and 0. Here, what we are using is basically a threshold on 7. Y less than 7, z is equal to 1, z is equal to 0. And the probability that z is equal to 1 is equal to my alpha, which is 0.72. Okay, so in this case here, if z turns on to be, okay, this is equal to 1. If it happens to be z equals to 1, then I am going to use a threshold test at 7. Gamma is equal to 7. Now, if z is equal to 0, then I'm going to use the other test where the threshold is placed at 6. Okay, so there's 1, 0. Okay, so as you can see here, so here is basically this happens with probability z equals to 0 equals to 28%. Okay, and here you use this. Okay, but there's a simpler way to write this. Okay, because you can see the following: x hat is equal to these cases here. Let me write this properly. Now, if y is bigger than or equal to 7, do I need to care about my coin? If y is bigger than or equal to 7, I don't need to care about my coin at all. I will always declare 1. All right, because okay, suppose my coin turns out 1. If y is bigger than 7, I will declare 1. If my coin turns out 0, and y is bigger than 7, I will also declare 1 here, because if y is bigger than 7, y is bigger than 6. So I'll declare 1 here. This is my rule. Similarly, if y is less than equal to 5, all right, if y is less than equal to 5, I don't need to care about my coin as well. I will always declare 0. I only need to talk about coins if y is exactly equal to 6. All right. If y turns out to be 6, I will toss my coin. Okay. So z here is equal to 1, z here is equal to 0. And in this particular case here, I will say 1 and 0. Okay. And this happens with probability alpha. And this happens with probability 1 minus alpha. Okay. So only with y equals to 6 do I need to care about my coin. I hope this is the right direction. I hope this is the right direction. Z equals to 1, y equals to 6. If y equals to 6, z is equal to 1. This is flipped, sorry. This is 0, 1. Right. If y is equal to 6, z equals to, sorry. What is this? Did I make a mistake here? So if y is equal to 6, I will declare, sorry, this is 1, 0 with probability. This is flipped here. 0, 1. This is with probability 1 minus alpha and alpha. Yeah. So this here corresponds to this line here corresponds to this here. Y is equal to 6. And this one here corresponds to this line here corresponds to here. Right, and z is equal to 1. So all is good. All right, sorry, I made a small little error just now, but hopefully everyone is following. And you will have a lot more exercises on this in the homework as well as the previous year exam problems. Okay, so this is all I want to talk about today, and thank you for attending. If you have any questions, we can talk about it. We can certainly talk about it anytime. Okay, we will have office hours next Thursday as well. But today, what we talked about was basically the optimality of threshold test through the Neyman-Pearson theorem. The theorem that we proved today is called the Neyman-Pearson theorem, or Neyman-Pearson lemma. I think it's called Neyman-Pearson lemma, but whatever. All right. Then we saw the notion of the error curve and the fact that all threshold tests lie on the error curve. Tests belong to error curve. But in the discrete case, all right, the error curve can contain points that don't correspond to threshold tests. Threshold tests. And we need to use randomization to achieve all points on the error curve. And randomization, you don't need to toss a dice. You only need to toss a coin. You only need to randomize between 2 threshold tests. Okay, so that is the summary for today. Hopefully you learned something. And I will see you at LT1 for those who turn up at LT1 next Friday, when we will go through estimation theory, which is not in the book. I wrote my own notes, but if you want to read ahead, I've already posted them. It's lec12.pdf. So we'll go through estimation theory. I do not know how long this will take because this is the first year I'm doing estimation theory. So it might take 1 lecture, it might take 1.5, but probably it won't take all 2 because I want to get to the main theorem there, which is the Cramer-Rao bound. Okay, I want to get to the Cramer-Rao bound there. And after I get to the Cramer-Rao bound, I will say goodbye to you. All right. Thank you very much. And we can meet at office hours as usual, or we can meet next Friday. I promise to only use 2 hours of time, so I will stop now. And the prerequisite knowledge required for estimation theory is everything that you have learned up to now. You need to know conditional distributions, right? Nothing much. Everything, if you understand up to this point, if you know basically probability at the level of lectures 1 to 3, you should be okay. I think so. Right? Sometimes if you are very keen, right, you need to know how to, you may want to know whether you can exchange when this is equal to this. Expectation exchange with integral. So sometimes you need to do this. Or can you differentiate under the integral? So maybe we will need to use some of this from my recollection, but I haven't prepared for next week's lecture yet. So I do not know what you need to know, but I think it's just probability and being comfortable in exchanging these linear operators. Okay, so I hope that answers your question, and remember to turn in the homework. Okay, thank you. Bye bye. Take care. Fluctuation means variance. Sorry, this is terrible. Okay. Compute the variance.
Okay, and Prof, I have another question, which is, I think in Gallager's book, right, they mentioned that the result still holds on possibly defective random variables condition on x equals 1. What does
Don't worry about defective random variables. I don't talk about defective things.
Oh, okay.
Yeah. I don't even know what are defective random variables. Right. I think defective random variables means random variables can take on plus infinity, right? From Gallager's book. But they have no applications in life, so I don't even know what they are.
Okay. Then for the exercises that we were given for this homework, right, are we required to use like knowledge from chapter 3? Because it seems that it's like
I think you need to use a little bit of knowledge about Gaussian random variables. So what do we need to know? I don't really know. So suppose you have Gaussian random variable x, and most what you need to know is what is the expectation and what is the variance of this sort of thing. But they should be direct generalizations of the scalar case. You can quote whatever results that you can find in chapter 3. Okay.
Okay, thank you, Prof.
You can quote whatever you like, but you can also look up Wikipedia for properties of Gaussian random vectors. No problem. Okay.
Yep. Thank you, Prof.
Okay, sure. Those people who want to leave can leave. I will also leave. Okay. Take care. I will upload these soon. Bye-bye. Bye.